Yeah. Either branch. Points out whatever. Time to front and back to the. Some kind of. You guys use it. Oh, yeah, you're not.
I just remember learning last year.
You didn't like edit. You guys really add to it.
I think I just like added to it. I really like the.
You guys know the magic. Yeah, I think that's like you probably just added at the end, right? But you added one, and it's putting you got feel like, but then you guys know. Yeah, just kind of, just kind of right point there. All these weird points there. No. Here, yes. Whatever you want. Honestly, last thing I think put a small rear is equal to. So like, here, and then you have rear and was starting at the joint, so you change from like that. That's something you. Yes. It's a lot of like, yeah, I like just a lot of those figuring out. Is you don't like creating error or like trying to understand like that. Like there's a couple of fire, mostly like the last one. Yeah, the music was.
All right, so it is 8:30. We have floating point arithmetic to get through. So just as a kind of recap or reminder, we did go over the floating points format last time. Have this format, right? We have bit is for the sign bits. The next 8 bits are for the exponents with the added bias, right? And then the last 23 bits are for the fractional parts of the significand. And the 1 is just implied, right? So what we want to be able to do is something like floating point addition. We consider a 4-digit decimal scientific notation example. If you have this number and you want to add this number, what's the first thing that we do? How do I add these two things together? What's the first step? Uh-huh. No. I'm saying in decimal. Like, how would you just normally do this? We want to align them, is what you're saying, right? So you can just multiply it out and get them both in the non-scientific notation form. But another way to do this is because I want to put it back into scientific formats, maybe keep one of them in scientific formats and just adjust the other to have the same exponent. Okay. So I want to, which one should I adjust? Should I adjust the bigger one to the smaller one or the smaller one to the bigger? So it's not really important which one, but because we are trying to keep in mind that we want to put it back into scientific notation, we want to adjust the smaller one to the bigger one because the smaller one will be adjusted by shifting the decimal to the left. And then when we add it to the bigger one, maybe it doesn't change it. Right? But if we adjust the larger one to the smaller one, we are for sure going to need to readjust back because it's shifting the decimal point to the right. So first step is align the exponents. And standard convention to reduce the number of steps is smaller one aligns with the larger one. So we adjust it like this, right? We shifted the decimal point to the left by 2, so we increase the exponent by 2. And now I can add the significant part with the significant part, right? We add them up, and then we get, this is our new result. And the next step is to normalize it, right? So to normalize this, what do I need to increase the exponent by? Just by 1. So it's now 10 to the 2, and I can move the decimal points so that it's 1.0015 times 10 to the 2. And then we would round and renormalize if necessary. Like we had 4 digits, 4 significant digits. We want to keep 4 significant digits. We round the 5 here up to make this a 2, right? And we have 10 to the 2. So we do the same thing in binary when we do rounding, except rounding in binary is simple, right? If there's a 1 that we're going to chop off, we just add 1 to the other one. If there's a 0 we chop off, we just chop off the 0. So with that in mind, if we wanted to, let's actually, did I remove a slide? Okay, I removed a slide, but we can just do this one together then. All right. And just so you do know, the poll is 204. You don't have to do this on your own right now, but we're going to do this one together. I just want to show you that the process is the exact same in binary, right? So we have 1.1101 times 2 to the 12 plus 1.0101 times 2 to the 14. So first step is align them, right? So which one am I going to move? And what's going to, how far am I going to move it? Which way?
2 spaces.
I have so that's 1, 2. That's my 0. This is my decimal. And then I have 1, 1, 1, 0, 1, and now I'm times 2 to the 14. Right? And then my next step is add them. So I have 1.0101, 0.011101. So I need to add 2 zeros here. 1 plus 0. 0 plus 0. 1 plus 1. 0. Carry the 1. 1 plus 1. 1 plus 1 plus 1.
1 carry 1.
1 plus 0. 1 plus 0. Okay. Times 2 to the 14. So this one would be A. We don't have to renormalize because it's already in its standard normal form. So we see how it's the same. Alright, let's also do one more step here. What if we had to keep the same number of binary digits? Like if we had to keep it as 1, 2, 3, 4, 5. What do we do here? So 1, 2, 3, 4, 5. It would just get chopped off. 2 to the 14. Okay. Alright, so multiplication. So floating point multiplication, again, going back to the decimal example. So what we all already know, what's my first step?
The small numbers. Actually, 10.
What's my first step here? That will result in the fewest number of steps.
You get rid of that, or try to even out the exponents, like subtract them.
Yes. Add the exponents together. Same base, right? So you can just add them together. Exponent. So my new exponent is going to be 10 to the 5. Right? And then my next step is that I can multiply the significance. So I would do this multiplied by that. I get 10.212 times 10 to the 5. Next step is so in this case, what do I need to do that? And
Increase the exponent.
normalize. And then if we want to keep the same 4 significant digits, what happens? I round, right? In this case, I round down. And then the other thing is we would determine the sign of the result from the sign of the operands. Basically, if they're the same sign, it's always positive. If they're different, it's going to be negative. So here is our floating points example. So we have 1.000 times 2 to the negative 1 times negative 1.110 times 2 to the negative 2. And this is their decimal equivalence. So first step, add exponents, right? So our actual exponent is going to be negative 3. And we're going to multiply the significance. So if we multiply 1.000 times 1.110, we get 1.110, right? And we have times 2 to the negative 3. Next step is normalize. We don't need to normalize in this case, right? And there's no change. And we would also round if we needed to. In this case, we just have our 4 bits, right? So floating point multiplication is very similar to just decimal, right? The only thing that you have to keep in mind is when you are using the exponents from the representation in the 32 bits, they have the bias, right? So if you add them together, you really have added the bias twice. So you should remember to subtract the bias once so that you keep 1. Okay? Or you can just subtract the bias from both of them and then add them and then re-add the bias in the end. The other thing is we needed to determine the sign, right? And it's positive times a negative, so result is negative. Right. So if we want to do 3 times 5, right? This is 3 in floating points and 5 in floating points. Add the exponents, multiply the significans, and then normalize and round if we needed to. But in this case, we're not doing that, right? And we determine the sign positive, positive gives us positive. All right, so here is another example. We have negative 1.0 times 2 to the 3 and 1.0 times 2 to the 4. Again, add the exponents. And here, this is what we're talking about to get the exponent bits. You can add them together directly, right? This is the exponent, this is the exponent. So if you add them together like that, you just have to remember, I need to remove my bias by 1. And then that gives me the correct new exponents, assuming that I don't need to normalize in the end, which has the bias in it. I'm going to multiply the significance. It's just 1 times 1, right? So I get 1, and we determine the sign. 1 was negative, 1 was positive, so the sign is negative. And then I didn't need to normalize, so I can use this result directly. But again, if you want to subtract the bias from both and then re-add it in the end, you can do that instead. All right, so that is our lecture for data representation and arithmetic. We have the rest of the time to work on homework 3. So homework 3, I printed out, I forgot to staple it. It's 2 pages. So if you want a hard copy, you can take this. It's also on Canvas. If you prefer to work on it digitally. But one thing about the homework is it is this fixed template. So provide your answers in the provided area. Do not use a separate sheet and turn that into Grayscale. And if you're going to work on it digitally, the Word document is again on Canvas, but make sure that you don't change the format of the document. All of the questions and the answers should be in the same place for everyone. Okay. Just as a reminder, do answer the poll 204 for the attendance. And the last thing before I let you guys just go, so I have 9 submissions for homework 2, but I only have 6 submissions for homework 1. Is anyone still waiting for like the email back? So everyone that is here has submitted homework 1. Did anyone change their group from homework 1 to homework 2? So I guess that is that. I will let you work on homework 3. Because we use some of the time today to finish the lecture, on Monday, I'll also give you the 50 minutes to work on homework 3. Because the goal is that you guys can finish this homework in the lecture time, so you don't have to go home and do it.